Hey guys, this video will be showing you how to answer questions 8 to 11 on a topic 12.2 formative assignments as part of our IB Physics HL curriculum. Let's just jump straight into it. Okay, so for question 8, list the 3 types of radioactive decay. There's alpha, there's beta, and there's gamma. For question 9, which of these 3 types has a pretty constant energy of about 4 to 5 mega electron volts? We have alpha. For question 10, which of these resulted in the predictions of the neutrino and why the neutrino needed to be present? We have beta. For question 11, which of these decay types is evidence for the existence of nuclear energy levels? We have gamma. I don't think that's good enough for a 4. Let's just get more serious, and here's the history of radioactivity. The studies of radiation have been prevalent throughout our extended scientific history. Notable findings such as Scottish scientist James Clerk Maxwell, who developed a unified theory of electromagnetism and predicted the existence of radio wave during the 1870s, to Röntgen, sorry if I completely butchered that name, infamously discovered the existence of X-ray, with the first ever X-ray rendition being a scan of his wife's hand. When we talk about the history of radioactivity, the first character who was inspired by Röntgen is Henri Becquerel in 1896. It is now very well recognized for phosphorescent experiment, where he wrapped a photographic plate in black paper with fluorescent salt and leave it under sunlight, with the hypothesis that the material absorbed the sun energy and remit it as X-ray. The results were negative until he had replaced phosphorescent with uranium in a cloudy Paris day, where his photographic plate was blackened by the radiation from uranium, proving that he has discovered a new form of radiation that does not rely on the external solar radiation. The then named Becquerel rays were chosen as the subject for Marie Curie and Pierre Curie doctoral thesis. The Curies, when trying to learn more about nuclear radiation, decided to tamper with pitchblende, or also known as uranium ore. They found out that some parts of the ore radiate more intensely than pure uranium, leading to the discovery of radium and polonium. They then coined the term radioactivity in the early 1900s. Just a few years later, Rutherford, while performing his most famous Geiger-Marsden experiment to demonstrate the nuclear nature of an atom, noticed that radioactive decay follows the same exponential mathematics, and that many such decay processes resulted in the transmutation of one element to another. These 4 great minds will forever be remembered as to have shaped our understanding of radioactivity. But what exactly is radioactivity? Radioactivity, or radioactive decay, describes the spontaneous deformation of unstable nuclei that lacks the binding energy necessary to hold the nucleus together due to an excess of either protons or neutrons. Because radioactive decay is determined by quantum mechanics, it is inherently probabilistic, hence we can only predict based on statistical analysis of large number of atoms. An unstable nucleus stabilizes by emitting excess energy in 3 main ways: alpha, beta, and gamma decay. The first 2 types of decay are transmutative in that the parent and daughter isotopes are different chemical elements. Let's go into more details on what the alpha decay is, and more importantly to why its energy is so consistent at 4 to 5 megaelectron volts, as to satisfy question number 9. Alpha decay, or alpha radioactivity, represent the disintegration of a parent nucleus to a daughter nuclide through the emission of nucleus of a helium atom. This is diagrammatically shown here, where isotope X with nucleon number A and proton number Z undergo transmutation to form an isotope Y with 4 fewer total nucleons as an energetic alpha particle is emitted. Properties of alpha particle include being relatively large and carrying a double positively charged, thus making them not very penetrating. In fact, a piece of paper should be able to stop them. Due to this fact, alpha decay is only observed in nuclides heavier than nickel and is common in all heavy radioactive nuclei in nature, such as your typical uranium, thorium, and radium. The alpha decay is also part of a quantum tunneling process in that the alpha particle must penetrate through a potential Coulomb barrier in a spontaneous process where the particle has a very small chance of tunneling through the said barrier after oscillating as an alpha cluster in a potential well of the daughter nuclei. Next, we can see here there's a sample calculation on how uranium-232 is transmuted into thorium-228 by alpha decay. By going through the calculations, you can see that the mass affected is about 0.006 atomic mass units, which can be converted into roughly 4.5 megaelectron volts. This number should be consistent with other isotopes going through the same radioactive decay process. Next, we need to examine the beta decay, which is a little bit more complicated. Beta decay represents the disintegration of parent nucleus to a daughter nuclei through the emission of a beta particle. The beta particle can be in the form of either an energized electron or a positron, which is indicated by either a positive beta or a negative beta sign, indicating either types of decay. Since beta particles are significantly smaller than alpha particles, they have a much greater range of penetration in the form of beta rays. Before we can try to explain question 10, let's look at the different types of beta decay, the first of which is the negative beta decay. In an electron decay, an unstable nucleus with excess neutron emits a negatively charged beta particles which decays further into an electron and an antineutrino. As an example, neutron-rich carbon-14 decays into nitrogen-14 with even numbers of protons and neutrons through beta decay. Alternatively, positive beta decay can be illustrated by how a proton-rich carbon-10 isotope decays into boron-10 by emitting a positively charged beta particle that decomposes further into a neutrino and a positron. The inverse beta decay, more commonly known as electron capture, is also classified as beta decay because it is also mediated by the weak force. In this example, a carbon-11 isotope absorbs an electron and decays into boron-11, and a neutrino is formed. The key difference between the alpha and the beta decay is that while both are transmutative, meaning that the parent and daughter are different elements, the mass number of the daughter nucleus in beta decay stays the same. Now we can use our basic understanding of the beta decay to explore question 10. Beta decay is governed by the weak interactions. For example, during negative beta decay, one down quarks will change into an up quark by emitting a negative W boson, which will then decay further into a combination of an electron and an antineutrino. Before we knew this, however, scientists were puzzled by the very small discrepancy in mass up to a few percentage of a megaelectron volts between the parent and daughter nuclei in beta decay. Wolfgang Pauli first suggested in 1930 that there was an invisible particle to explain how beta decay could conserve energy, momentum, and spin. This invisible particle is now coined as the neutrino, but its true nature is still remain largely unknown. Our last but certainly not least medium of decay is the gamma decay. Gamma radioactivity represents the disintegration of a parent nucleus to a daughter nuclei through the emission of a high energy photon ray. In this diagram, we can notice several key points about the gamma decay. First, gamma decays take place in an excited and unstable nuclide that are looking to stabilize by emitting a gamma rays from its nucleus. By this definition, the process is not transmutation. This is because the fact that the daughter and the parent's isotope are identical but just in different energy states. The gamma decay typically accompanies the alpha and beta decay in that it will happen after the aforementioned decay types to stabilize the excited daughter isotope that contains too much energy to be in its final states. In contrast to the alpha and beta radioactivity, gamma decay is governed by the electromagnetic interaction. By knowing this, we can look at how gamma decay is involved in an isometric process, which is often indicated, as you can see in the diagram, by a superscript letter M, such that isotope X with nucleons number AM. In this following diagram, we can see the decay scheme of isotope iodine-131 into xenon of the same atomic mass number. Notice that the iodine isotope goes through a beta decay first before an isometric process takes place to de-excite the newly formed xenon isotope, releasing the gamma ray with energies that range from a few megaelectron volts to up around 8 mega-electron volts, depending on the energy levels of the excited states of the parent nuclide. Gamma decays provide evidence for discrete energy levels since both the parent isotope and the daughter isotope have fixed masses. The gamma produced should have single energy defined by the mass difference in the reaction, hence satisfying question number 11. I have now adequately answered and explained all four questions 8 to 11 in our 12.2 formative assignments. This video is 3 days overdue, but I had to retaught myself the chapter, so it took longer than expected. But I still hope this video has been very informative. Maybe you can show it to your future students so that they can laugh at my paper 1 grade. Anyhow, thank you for watching and good luck in your future pursuits beyond AIS, Mr. Cryer, and whatever that may be. Thank you.